When addressing a 600 amp feed without a ground wire, several options can be considered to ensure proper grounding and compliance with the National Electrical Code, or NEC. The distance of the run, being 300 to 400 feet, and the use of rigid metal conduit, or RMC, are important factors in evaluating these options. One option is to utilize the existing conduit as a grounding conductor. This can be a cost-effective and straightforward approach, as it eliminates the need for additional materials. However, its acceptability hinges on meeting specific criteria. Firstly, the conduit must be either electrical metallic tubing, or intermediate metal conduit, or IMC, or rigid metal conduit, or RMC. Secondly, the conduit should be in good condition, free from breaks or holes that could compromise its electrical continuity. Thirdly, it must be properly bonded to both the switchgear and the motor control center, or MCC, to ensure a reliable grounding path. Fourthly, the conduit should not be used for any other purposes, such as carrying signal or power cables unrelated to the 600 amp feed, as this could interfere with its grounding function. Another option is to run a separate conduit specifically for the ground wire. This approach offers the advantage of ensuring a dedicated grounding path which aligns with the NEC requirements for grounding. Running a separate ground is generally the preferred solution if the existing conduit cannot be verified to meet the criteria for use as a grounding conductor. While providing a reliable grounding solution, running a separate conduit entails additional costs for materials and labor. It may also present installation challenges, particularly in existing facilities where space and access may be limited. Another method involves installing parallel grounding conductors. This approach provides redundant grounding paths, enhancing the overall reliability of the grounding system. By using multiple grounding conductors in parallel, the impedance of the grounding path may be reduced compared to relying solely on the conduit. However, implementing parallel grounding conductors is generally more expensive than other options, as it necessitates additional materials and labor for installation. It may also require careful consideration of conductor sizing and spacing to ensure proper current sharing and minimize inductive reactance. Alternatively, a supplementary grounding device can be installed. This option is particularly useful in situations where the conduit is not suitable for use as a grounding conductor or where additional grounding redundancy is desired. Supplementary grounding devices, such as ground rods or grounding electrodes, provide a reliable grounding path independent of the conduit system. While offering a versatile grounding solution, installing a supplementary grounding device requires additional materials and labor. It may also necessitate coordination with the utility company, especially if the device is connected to the utility's grounding grid. When making a recommendation, if the existing rigid metal conduit, or RMC, meets the criteria for use as a grounding conductor, it represents the most practical and cost-effective solution. However, if the existing conduit does not meet the necessary requirements, running a separate conduit for the ground wire is generally the preferred solution, as it ensures compliance with the NEC and provides a dedicated grounding path. According to the National Electrical Code, or NEC, a grounding conductor must be installed with all ungrounded conductors in a raceway. However, a metal raceway can be used as a grounding conductor if it meets specific requirements. These requirements include being electrically continuous and securely bonded to the equipment it serves, ensuring a low impedance path for fault currents. The metal raceway must also be of adequate size, not smaller than the size required for the grounding conductor to effectively carry fault currents back to the source. Additionally, the raceway must not be used for any other purpose besides serving as a grounding conductor to prevent interference with its grounding function. Consider a scenario where the 600 amp feed is supplying power to a large piece of machinery in an industrial facility. The original installation lacked a dedicated grounding wire, relying solely on the metal conduit for grounding. Upon inspection, it's discovered that the conduit has several sections that are not properly tightened, creating points of high resistance. In this case, using the existing conduit as a grounding conductor would not be advisable due to the compromised electrical continuity. The preferred solution would be to run a separate grounding conductor within its own conduit, ensuring a reliable and dedicated grounding path for the 600 amp feed. This would involve selecting the appropriate size of grounding conductor based on the size of the ungrounded conductors, as specified in the NEC Table 250.122. The grounding conductor would then be installed in a separate conduit running parallel to the existing conduit and securely bonded to both the switchgear and the machinery. In another scenario, imagine the 600 amp feed is supplying power to a critical piece of equipment in a hospital. The existing conduit is in good condition and meets all the requirements for use as a grounding conductor. However, due to the sensitive nature of the equipment and the potential consequences of a grounding failure, it's decided to implement a supplementary grounding system. In this case, a ground rod is installed near the equipment and connected to the equipment grounding bus. This provides an additional grounding path, enhancing the overall reliability and safety of the grounding system. The NEC provides specific guidelines for the installation and sizing of grounding electrodes such as ground rods in sections 250.52 and 250.53. The size of the grounding electrode conductor would be determined based on the size of the service entrance conductors, as specified in NEC Table 250.66. When evaluating grounding options, it's essential to consider the specific characteristics of the electrical system, the environmental conditions, and the potential risks associated with the grounding failure. A thorough understanding of the NEC requirements for grounding is crucial in ensuring the safety and reliability of the electrical system. The NEC specifies requirements for sizing grounding conductors, bonding metal enclosures, and grounding sensitive electronic equipment. The selection of the appropriate grounding method should be based on a comprehensive assessment of these factors. When running a separate grounding conductor, it's important to consider the impedance of the grounding path. The impedance of the grounding path should be as low as possible to facilitate the rapid clearing of ground faults. High impedance grounding paths can limit the flow of fault current, delaying the operation of overcurrent protective devices and increasing the risk of electrical shock or fire. To minimize impedance, the grounding conductor should be as short and straight as possible, and all connections should be clean and tightly made. The use of exothermic welding for grounding connections can provide a low-resistance, corrosion-resistant connection that enhances the reliability of the grounding system. In some cases, it may be necessary to perform a ground impedance test to verify the effectiveness of the grounding system. A ground impedance test measures the impedance of the grounding path from the equipment to the source of power. The test results can be compared to the maximum allowable impedance values specified in the NEC to ensure that the grounding system is adequate. If the measured impedance exceeds the allowable limits, corrective action should be taken to reduce the impedance of the grounding path. This may involve improving bonding connections, adding additional grounding electrodes, or rerouting the grounding conductor to shorten the length of the grounding path. The NEC also addresses the grounding of sensitive electronic equipment, such as computers and communication systems. Sensitive electronic equipment can be susceptible to damage from voltage transients and electrical noise. Proper grounding is essential to protect this equipment from damage and ensure reliable operation. The NEC recommends the use of isolated grounding systems for sensitive electronic equipment. An isolated grounding system provides a separate grounding path for the equipment, isolated from the building's normal grounding system. This helps to minimize the flow of electrical noise and voltage transients into the equipment, reducing the risk of damage or malfunction. The isolated grounding conductor is typically run in a separate conduit from the normal grounding conductors and is connected to a dedicated grounding electrode. The NEC also provides requirements for bonding metal enclosures and equipment to the grounding system. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electrical shock. Metal enclosures, such as electrical panels and junction boxes, should be bonded to the grounding system using bonding jumpers or other approved methods. The bonding jumpers should be sized according to the requirements of the NEC and should be securely connected to the metal enclosures. In corrosive environments, it may be necessary to use special bonding methods to prevent corrosion of the bonding connections. The NEC also addresses the grounding of hazardous locations, such as areas where flammable gases or vapors may be present. In hazardous locations, special grounding requirements apply to prevent the accumulation of static electricity and reduce the risk of explosion. The grounding system in a hazardous location must be designed to provide a low impedance path for fault currents and to minimize the risk of sparking. The NEC requires the use of intrinsically safe grounding systems in certain hazardous locations. Intrinsically safe grounding systems are designed to limit the amount of energy available in the circuit, preventing the ignition of flammable gases or vapors. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be inspected periodically to ensure that they are clean and tight. Grounding conductors should be checked for damage or corrosion. Grounding electrodes should be tested to verify their effectiveness. Any deficiencies in the grounding system should be corrected promptly to maintain the safety and reliability of the electrical system. The NEC requires that a record of the grounding system be maintained, including the location of grounding electrodes, the size of grounding conductors, and the results of grounding tests. This record should be readily available for inspection by qualified personnel. In summary, grounding a 600 amp feed without a ground wire requires careful consideration of several factors, including the type of conduit, the condition of the conduit, the presence of other conductors in the conduit, and the environmental conditions. The NEC provides specific requirements for grounding electrical systems, and these requirements must be followed to ensure the safety and reliability of the system. The option of using the existing conduit as a grounding conductor is acceptable only if the conduit meets certain criteria, including being electrically continuous, securely bonded, and not used for any other purpose. Running a separate conduit for the ground wire is generally the preferred solution, as it ensures a dedicated grounding path and complies with the NEC requirement. Other options, such as installing parallel grounding conductors or a supplementary grounding device, may be considered in certain situations. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. When evaluating grounding options, it's important to consider the specific characteristics of the electrical system, the environmental conditions, and the potential risks associated with a grounding failure. A thorough understanding of the NEC requirements for grounding is crucial in ensuring the safety and reliability of the electrical system. The NEC specifies requirements for sizing grounding conductors, bonding metal enclosures, and grounding sensitive electronic equipment. The selection of the appropriate grounding method should be based on a comprehensive assessment of these factors. Furthermore, when dealing with a 600 amp feed, the size of the grounding conductor is critical for safety. NEC Table 250.122 dictates the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. For a 600 amp feed, this will require a substantial grounding conductor, often larger than what might be intuitively expected. This is to ensure that the grounding path can effectively carry fault current back to the source, allowing the overcurrent device to quickly trip and clear the fault. Additionally, consider the impact of voltage drop on the grounding system. While voltage drop is often associated with the power conductors, it can also affect the performance of the grounding conductor, especially over long distances. Excessive voltage drop in the grounding conductor can impede the flow of fault current, delaying the operation of the overcurrent device and increasing the risk of electrical shock. To mitigate voltage drop, the grounding conductor should be sized appropriately and installed in a manner that minimizes its impedance. In addition to the NEC, other standards and guidelines may provide valuable information on grounding practices. For example, the IEEE Standard 142, commonly known as the Green Book, provides recommendations for grounding industrial and commercial power systems. This standard covers a wide range of topics, including grounding system design, grounding electrode selection, and grounding system testing. Consulting such resources can provide additional insights and best practices for ensuring effective grounding. When making grounding modifications or upgrades, it is important to document all changes and maintain accurate records of the grounding system. This documentation should include the location of grounding electrodes, the size and type of grounding conductors, and the results of any grounding tests performed. Accurate records are essential for troubleshooting grounding problems and ensuring compliance with regulatory requirements. Grounding is not a static aspect of an electrical system. It requires ongoing monitoring and maintenance. Changes in the electrical system, such as the addition of new equipment or modifications to existing circuits, can affect the performance of the grounding system. Therefore, it is important to periodically review the grounding system and make any necessary adjustments to ensure its continued effectiveness. The principles of grounding extend beyond the specific scenario of a 600 amp feed without a ground wire. Grounding is a fundamental aspect of electrical safety and is applicable to all electrical systems, regardless of size or complexity. Understanding the principles of grounding and the requirements of the NEC is essential for anyone working with electrical systems. Proper grounding is not just a matter of compliance, it is a matter of safety. It protects people from electrical shock, prevents equipment damage, and reduces the risk of fire. By following the best practices for grounding, you can create a safer and more reliable electrical system. Remember that improper grounding can have serious consequences, including electrical shock, equipment damage, and fire. It is always best to consult with a qualified electrical professional to ensure that your electrical system is properly grounded and meets all applicable codes and standards. Grounding is a complex topic, and it is important to stay up to date on the latest codes and standards. The NEC is updated every 3 years, and it is important to be aware of any changes that may affect your electrical system. Continuous learning and professional development are essential for maintaining a safe and reliable electrical system. The goal of grounding is to provide a low impedance path for fault current to return to the source, allowing the overcurrent protective device to quickly clear the fault. This minimizes the amount of time that a person is exposed to hazardous voltage and reduces the risk of electrical shock. A well-designed and properly installed grounding system is an essential component of a safe and reliable electrical system. Firstly, ensure the integrity of all connections. A loose or corroded connection can significantly increase the impedance of the grounding path, reducing its effectiveness. Secondly, use the correct tools and techniques when making grounding connections. Improperly installed connections can be just as bad as no connection at all. Thirdly, visually inspect the grounding system on a regular basis to identify any signs of damage or deterioration. Fourthly, test the grounding system periodically to verify its effectiveness. A simple continuity test can identify open circuits or high resistance connections. Fifthly, document all grounding system inspections, tests, and repairs. This documentation will be helpful for troubleshooting problems and ensuring compliance with regulatory requirements. Sixthly, follow the manufacturer's recommendations for grounding equipment. Some equipment may have specific grounding requirements that must be followed to ensure safe and reliable operation. Seventhly, consider the impact of electromagnetic interference, or EMI, on the grounding system. EMI can cause noise and interference in sensitive electronic equipment, and a properly designed grounding system can help to mitigate these effects. Eighthly, be aware of the potential for ground loops. Ground loops can cause circulating currents in the grounding system, which can lead to noise, interference, and even equipment damage. Ninthly, use appropriate surge protection devices to protect equipment from voltage transients caused by lightning or other events. Tenthly, consult with a qualified electrical engineer or electrician if you have any questions or concerns about grounding. Grounding is a critical aspect of electrical safety, and it is important to get it right. Implementing regular inspection and maintenance procedures ensures a robust grounding system that provides continuous protection. This proactive approach minimizes the risk of electrical hazards and enhances the overall reliability of the electrical installation. By consistently adhering to these practices, one can ensure a safe and efficient electrical environment. This attention to detail not only safeguards personnel, but also protects valuable equipment from potential damage, underscoring the importance of diligent maintenance and electrical safety. This maintenance should include checking for any signs of wear and tear on grounding conductors and connections, as well as verifying that all grounding points are securely fastened. Regular testing should also be performed to measure the impedance of the grounding path and ensure that it remains within acceptable limits. Any deviations from these limits should be promptly addressed to maintain the integrity of the grounding system. The proactive approach not only helps in preventing electrical accidents but also contributes to the longevity and optimal performance of electrical equipment. This results in reduced downtime, lower maintenance costs, and increased productivity. By investing in regular inspection and maintenance, one can create a safer and more efficient electrical environment that benefits everyone involved. The meticulous inspection and maintenance of grounding systems are paramount in ensuring electrical safety and operational efficiency. Therefore, one should always prioritize and allocate adequate resources to these critical tasks.